Number 69 is a red level problem. Again, just a quick reminder, red level problems are considered more difficult than even an AP question. But I gave you this one knowing that you could probably do it. Let me just quick explain. We've got a neutron interactor makes an elastic head-on collision with a carbon atom that's initially at rest. The mass of the carbon nucleus is about 12 times that of the neutron. A, what fraction of the neutron's kinetic energy is transferred to the carbon nucleus? So we've got an elastic collision here. You don't know the masses, but we do know that the initial velocity of the neutron, which I'm going to say its mass is m, is going to collide with the stationary carbon nucleus, which has a mass of 12m. So its initial velocity is 0. What's going to happen afterwards? Well, the neutron should rebound with some final velocity. I'm calling it v1 final. And the carbon nucleus is going to move with some final velocity, v2 final. We need to find this velocity so that we can actually calculate the final kinetic energy of it. To do that, I'm going to have to do an elastic collision. Remember, the easiest way, we could do simultaneous equations both for momentum and kinetic energy, but let's do the easy way with the center of mass. In this case, the velocity of the center of mass is the total momentum, which is just the momentum of the neutron before the collision, divided by the total mass, which is the sum of the mass of the neutron and the carbon nucleus. M cancels out, and you just end up with 1/13 of its initial velocity, or of the initial velocity of the neutron. So the center of mass is not moving very quickly, just because the carbon nucleus is stationary and it's so massive. To find the final velocity of the carbon nucleus, I'm going to use, this equation would give us the final velocity of the neutron. But in this case, I'm actually interested in the final velocity of the carbon atom. So V2 final is 2 times the velocity center mass, the 1/13 V10, minus the initial velocity of the carbon nucleus, which in this case is 0. And so in this case, 2/13 times the V0. This is going to be the final velocity of our carbon nucleus. But that's not where we're interested in. We're interested in the energy. So I guess I could write over here. This is, well, yeah, let's just do it. We know what that is. So the initial energy of our system is this. 1/2 the mass of our neutron times its initial velocity squared. What's our final velocity? And my apology, or final kinetic energy, my apologies, this looks a little scary. Here is 1/2 mv squared. We're only interested in the kinetic energy of the carbon nucleus. Its mass is 12m. Its velocity is this that we just found down here. We're plugging it in, we have to square it. I'm going to do a little weird math. I'm going to leave the 1/2 out front. So 2 squared is 4 times 12 gives us 48. And 13 squared is 169. I'm going to write it this way. And you might say, whoa, why'd you write it that way? Well, take a quick look at this. This is 1/2 m, 1/2 m, and then we have v1 initial squared, v1 initial squared. Oh, how do these differ? Well, they just differ by this fraction, 48 over 169. The final kinetic energy of this is going to be 48 over 1/69 of the original kinetic energy of the neutron. Converting that to a decimal and then to a percentage, the correct answer is only about 28.4% of the neutron's energy is going to be transferred to the carbon nucleus. That's the answer to A. You're like, holy cow, that was a lot of work for just A. Yeah, this is why it's a red level problem. But B is actually not too bad. B, they give us the neutron's initial energy, and we have to find the final kinetic energy of both it and the carbon nucleus. But now it's plug and chug. Solving this one, we know that the carbon nucleus is going to get 28.4% of the neutron's energy. So just plugging it in, 28.4% of that initial energy gives us that. And then for the neutron is going to get all the remaining energy. This is an elastic head-on collision. We're assuming no E-dis at all. And I guess that's part of it what makes it a red level problem. And so if 28.4% went to the carbon atom, all the rest of it stays with the neutron in its recoil backwards here. And just plugging in our numbers, you'll get that final energy there. So here is the final energy of the carbon nucleus in this case, and this is the final energy of the neutrino. You might say, whoa, wait a second. It looks like the carbon nucleus got more energy than the neutrino. Yeah, look at the powers though real quick. This is 11.5 times 10 to the minus 14th compared to 4.5 times 10 to the minus 14th. Yeah, it is a little different. Yeah, it's a red level problem. It is a little more challenging, especially with all the variables. If they had simply given us numbers, this would have been much more tolerable. See you soon.